Hello, viewers. We are right now streaming live, and welcome to another interesting episode of the semiconductor webinar. Today, we have Rajit with us. He is currently studying in the third year of Electronics and Communication Engineering at Bapuji Institute of Engineering and Technology. Rajit has a presentation today, and he will be narrating the next part. So, over to you, Rajit.
Okay, greetings to everyone. My name is Rajit H. I'm an EC student at Bapuji Institute of Engineering and Technology. I'll be starting third year of engineering in a week, and I have my interests in VLSI and digital design. I'm still learning, and I really enjoy working with practical projects. So in this session, I'll walk you through the digital circuit 64-bit barrel shifter. It's a digital design. It's digital design and simulation using Verilog HDL. And before getting started, I'd like to thank Mridul Sengupta sir and Tech Simplified TV for providing this platform for students. I'm glad to be a part of it. So let's get started. So moving on to introduction of the barrel shifter. So a barrel shifter is a combinational digital circuit that shifts the bits of its input data by a specified number of position in a single shot. So an obvious question which arises is, why do we need another shifting circuit when we already have shift registers, right? Universal shift registers, right? The problem is universal shift registers can shift one bit per cycle, whereas a barrel shifter can shift multiple bit in a single shot. So this is the main difference which helps in uh, various applications which are listed as follows. So some applications I have listed here, going through them. So first one is ALUs in microprocessors. So for operations like multiplication and division, where okay, so in microprocessors, so ALUs in microprocessors for operations like multiplication and division being performed with respect to powers of two, a barrel shifter is useful. As we know, a binary value when left shifted by k bits is equivalent to being multiplied by 2 power k. Similarly, a binary value being right shifted by k bits is equivalent to be divided by 2 power k. So when dealing with these operations in powers of 2, we don't need a dedicated multiplier circuit. A barrel shifter can efficiently handle this. So moving on to the next application, which is a DSP processor. In signal processing, uh, we often have to scale a signal, nothing but we bring a signal to a required range. That means adjusting the amplitude or magnitude of a signal. It is a basic operation which comes up in DSP, where a sample in a signal is multiplied by a constant value. That constant value is known as a scaling factor. So when it is in powers of 2, we can use a barrel shifter as its application. So the next one which you come across is cryptographic hardware. Right. Barrel shifters are important block in cryptographic hardware that allows to perform faster shifting for efficient implementation of the shift-based permutations. There are some bit permutations which will occur. So a barrel shifter is crucial for speed and performance. So moving on ahead, we have a GPU, a graphics processing unit. So here pixel manipulations come into picture. So GPUs are designed in such a way that they are capable of processing huge amount of data parallelly. So these often have to deal with pixel manipulation that require bit alignment, masking, and fast shifting, which is done using a barrel shifter. It plays a role in speeding up the certain bit level operations. And in GPU, a barrel shifter is not a core component, but it's just a component which can help in enhancing the efficiency. So moving on ahead, we have communication systems. So barrel shifters play an important role in communication systems, particularly in data alignment and bit level tasks. They help to align the incoming serial data. If you consider serial communication, the incoming data needs to be aligned properly into proper byte or word boundaries as defined by the protocol. Their ability to shift multiple bits of data in a single go makes it essential for high speed communications. So these are some applications which we see here. And one thing to note is overall in a so overall all there is all a barrel shifter does is shifting the bits. That's all is happening, nothing more. So moving on to the next slide, we have the input output signals. So as you can see in the slide, a schematic is provided. So we define this design as a Verilog module. with set of inputs and a single output. So the inputs are as follows: input data, the data word on which shifting is to be performed. This word is given by the user on which the shifting operation is being performed. So the next input is the shift direction, specifies whether to shift the data in left direction or in right direction. Uh, Here I have used a convention, a simple convention, where dir, if it is equal to 0, it is left shift. If dir is equal to 1, it is right shift. Of course, you can change the convention as well. So the next input is the shift amount, which specifies how many bits of position is to be shifted. So since the shifting range is from 0 to 63 bits, 2 power 6, which is 64, so 6 bits of value can clearly specify the shift amount which is needed. So next input is the sign bit. This determines the type of shift during the uh, when the operation is going on. Like say in case of signed numbers, we have to make sure that the MSB bit is being extended while right shifting. This is necessary to maintain its actual value. In case of unsigned numbers, there is no specific need to mention sign bit. We can simply mention it as 0. So coming to the output signals, there is one output, D out, which is a 64-bit output, which is the final shifted value given out from the design. So next, moving on to the design. So before jumping straight away into a 64-bit design, let's simplify it and take a look at 8-bit design to understand the logic. So the input here is a 8-bit word DIN, and we want to shift it by a certain number of positions based on a 3-bit control input control input value. Here I have defined it as val. That means we can shift the data from 0 to 7 bits. So shifting operation is divided into 3 stages. If you consider it from left to right or right to left, you can see multiplexer stages. So if I consider it from right, the first stage shifts by 1 bit controlled by val 0. The second stage shifts by 2 bits controlled by val 1. The third stage shifts by 4 bits controlled by val 2. Each stage is made up of multiplexers that decide whether to pass the data as it is or whether to shift it by the stage's corresponding value. For example, say if val 1 is high, the second stage will shift the current data by 2 bits. And one more interesting thing to note here is the shifting doesn't happen sequentially. It's a combination of circuits. So it's not like we shift 1 bit, then shift 2, and so on. All stages work in parallel, and the output is ready just in one cycle. That's why it is a faster circuit compared to a normal shift register. So after understanding logic, let's move on to a 64-bit design. A schematic is shown here. So the structure is very much similar to a 8-bit version. Just the thing is, it's larger with more stages of multiplexing. Since we're dealing with 64, we need to support shift from 0 to 63. This is the range in which we can shift the data. So that's why we have 6 stages, each responsible for shifts by 1 bit, 2 bit, 3 bit, 1 bit, 2 bit, 4 bits, 8 bits, 16 bit, and 32 bits. So we can note that this goes in powers of 2. So each multiplexer stage is corresponded with 1 bit of value. These multiplexers selects between the current value and the value shifted by the powers of 2. And you can see that the DIR signal, the direction signal, is also connected with subsequent multiplexers here, which decides whether to left shift or right shift. So just like an 8-bit design, a 64-bit barrel shifter can shift any number of bits in constant time using combinational logic. So there is no, see, ideally there won't be any delay. The only delay which we come across here is the gate delay. So the logic will remain the same, only the width of the design will increase. And for a barrel shifter, the shift amount width is log 64 of base 2, which is 6 bits, to get a range of 0 to 63. So once we take a look at the Verilog code, we'll go through these test cases mentioned here. So which will be negative number division, positive number division, negative number multiplication, positive number multiplication, and scaling a signal. These are just some example values I have mentioned here. And even if you change the values, the output will be the correct one. And note that this is not a actual verification. This is just a dummy test cases I have selected to check out the shifting behavior of the design. So I'll be presenting my screen from here.
So yes, yes. Let me add it to. So yeah. So can you lower the browser? Yeah. Now it is okay. I'll add. It. Screen is there. Yeah. I think it is okay.
Okay. So here we have the barrel shifter Verilog code. So this is the module declaration, and these are the input-output ports, and the corresponding ports are declared are specified as input or output here. So DIN is the 64-bit input value. Val is the shift amount, which is in 6 bits, and direction and sign are single-bit values, which represent whether to hold the sign, whether to consider the sign bit, and DIR is the direction, and the output is the D out, which is also 64-bit. Then we see some wire declarations here. These are the intermediate connections which we see between the multiplexer stages. So here LS corresponding to left shift and RS corresponding to right shift. And these are the intermediate multiplexer output wires. And one more thing we can notice here is this is the replication operator. Means whatever is mentioned here will be replicated the number of times mentioned here. So here I have mentioned one tick binary 0, indicating a 0 value, which is being replicated 64 times and assigned to a wire 0. And here you can see this is also a replication operator, but I have used the expression here to calculate whether to extend it with the MSB bit or whether to substitute zeros in the shifted values. So this will come in handy while dealing with right shifting and considering the sign bit. So next we have a set of assign statements here, which will declare the values for the respective shifted values. So LS1 is a 32-bit shifted version. LS2 corresponds to 16-bit shifting. LS3 corresponds to 8-bit shifting. LS4 corresponds to 4-bit, and LS5 corresponds to 2 bits, and LS6 corresponds to a single bit left shift. Similarly, we have the wires for right shifting, and note that here we use the E wire declared over here. So nothing but extension bits. In case of right shifting, we happen to extend it with either 0 or 1 as calculated by this expression. And sign and DIN. So DIN 63, this is the MSB bit of the input value, and sign is the bit we have explicitly mentioned, whether to consider the MSB or to simply substitute zeros. So moving on further, uh, here we have module instantiations of multiplexer. So this is another module for multiplexer which is declared here, and I have used a simple ternary operator to specify the 2:1 multiplexer behavior. If select is 1, CS1 is assigned to out. If select is 0, CS0 is assigned to out. And note that the positions of the ports matter, because the first port is the output, second is the select line, and third and fourth are the inputs given to it. So these are the multiplexer stages. As you can see, B1, BM1, B2, BM2. Similarly, up to 6 stages are defined here. So as shown in the schematic, this is how it is connected using Verilog. So moving on to test benches. So here I have several test cases as shown in the PPT previously. So first we'll be dealing with negative number division. So this is some random value I have chosen. It can be different as well. So if we check the output for this, as you can see, this is the negative number division. So this number is being divided by 2 power 5. And as you can see, this is a right shift operation, and we are considering the MSB value. Nothing but it is a negative number, signed number. If you check the output, the radix of these values are set in signed decimal so that we can clearly identify it. So 70,496 divided by 2 power 5, 32, will give you 2203, and it will be a negative value. If you just take a calculator and happen to calculate it, it will be the same value. So this indicates that the right shifting is working fine. So the next test case is positive number division. So 20,984 divided by 2 power 2, and direction is right side, and this is a unsigned number. We are not considering the sign here. And if you check out the output, that would be 5246. If you happen to take a calculator and compute it by dividing this by 2 power 2, which is 4, you'll get the same value. The next test case is a negative number multiplication. So this is the number I have chosen, 64,213 with negative sign, which is being multiplied by 2 power 3. And direction is 0, indicating left shift, and sign is 1. Nothing but we have to consider the MSB bit for extending. And if you check the output, we get something like this, which is the correct value when checked with the calculator. So the next test case is positive number multiplication. This is the number I have chosen, which is being multiplied by 2 power 4. So direction is 0, indicating left shift, and sign is 0, indicating this is unsigned and need not consider the MSB bit. And if you happen to check the output, we get something like this. So here it is 4521 into 2 power 4, which is 16, and we'll get the answer as this. So the next test case, scaling a signal by a factor of 4. So this is a dummy value I have selected. It can be different. So scaling the signal by a factor of 4, in the sense we are multiplying it with 4. The scaling factor is 4, so which is represented as 2 power 2 here. Direction is 0, indicating left shift, and the sign bit is 0, indicating no need to consider the MSB bit. And the output, we happen to get it something like this. And for the next test case, we have scaling a signal by a factor of 0.125. So this is the same signal value as chosen previously here. But the thing is, we'll be scaling it in the factor of 0.125. So it's like division with 2 power 3, where direction is 1, indicating right shift, and sign bit is 1, indicating we have to consider the MSB bit. And the output happens to be like this. So the test cases are proven in this waveform window. So the design is working fine. And note that this is only a simple test bench to verify its shifting behavior and not a actual verification process. So this is the schematic being, this is the schematic which was implemented using the Verilog code. So this concludes my presentation. Thank you.
So, thank you, viewers, for attending the session live, and we are open for questions. And one question from my side to Rajit is that when you are designing such digital circuits, from where do you start, and how do you think what should we give as input vectors? So, if you can tell us that.
It depends on the logic which we have to implement, sir. So first, we need to go through the circuit. We need to understand the logic behind it, how it works. So, and implementing in Verilog is, of course, based on practice. It depends on the programmer, sir. The more we practice, the better design we are able to create. So reducing redundant hardware is very much important to optimize it so that it uses lesser number of gates. So that's important here.
Okay, great. So I think viewers also enjoyed the session, and I don't see any question came. I think everyone was in absorption mode. So people actually was absorption, doing the absorption of your knowledge transfer through the session. So I think, and I would like to thank to all of viewers who attended live, and also in advance thankful who will be watching it later. Today we had we had a session of the semiconductor webinar where our digital circuit is presented. So one thing I'd like to say here, that in the actual verification arena, this circuit will be surrounded by a lot of other blocks. So this is a kind of block level verification using a Verilog test bench. And when we go for the digital verification, there we use our verification methodologies, like the name of the UVM, OVM, etc. for the full chip verification, you can say. And this block level verification is good, very good for individual blocks when they are designed, and when these blocks are put together we go for a digital verification. So that is a different thing, and here we have done it using Verilog, and the other, that is the total chip level verification, is done through the system Verilog. So we'll not go in that direction right now, but just for your knowledge, so that you have the clarity. We had gone through the today's session, and thank you, Rachit, for spending your time for sharing knowledge to the community. In the semiconductor webinar, we encourage the knowledge sharing, that is, in another word, it is called the peer learning. And when you students learn from your peers, so that means you are learning from another student, and this is our global channel. So we are having students from at least different parts of the India. I think today, Rachit, from where you have joined, from which location?
Karnataka, sir, India.
So
Karnataka,
you are
Davangere.
from, yeah.
Yes.
So Rachit joined today from Karnataka. Previously, Lakshmi joined from Tamil Nadu, and Bhavesh and Jayasri, they also joined. They were joined from Gujarat. So this way, we are encircling the entire country right now, and students from different part of India, they are sharing their peer learning process, and this is how you come to know about different things your peers are doing. So the student can be from any other university, any other college, and either they could be undergraduate or the postgraduate level. So people, that means specifically students, they are learning from their peers. So we encourage peer learning through the semiconductor webinar. And thank you for attending, and Rachit, thank you too for presenting today. And we will say bye to the viewers because we don't have any questions right now. So we will meet in another interesting episode of the semiconductor webinar in upcoming weeks. So stay tuned, stay focused, and Rachit, have a very good night. And viewers also, we are saying you have a very good night. So bye for
Glad to be
today.
a part of the webinars. Thank you.